At this point, we've talked about 4 different circuit elements. We've talked about the battery, a resistor, a capacitor, and an inductor. What I want to do now is highlight the similarities between 2 of those elements. If we think about how we might talk about the purpose of each of those 4 elements within a circuit, well, the purpose of a battery is to provide energy that drives the current. The purpose of a resistor, of course, is to dissipate energy running through it. Right? It converts that electrical energy into thermal energy within the resistor. The capacitor and the inductor, on the other hand, their purpose is to store energy. So both of them have the same basic function. They simply choose to do it in different ways. So a capacitor stores energy within an electric field. An inductor stores energy within a magnetic field. So what we want to do in this next video is talk about what are some similarities that we can see between a capacitor and an inductor, and how that might help us think about what an inductor is doing within a circuit. So again, let's jump back to thinking about a capacitor. We know that we make a capacitor by separating 2 conducting surfaces, and if we choose to, we can tuck an insulator into the space between them. So I've got my 2 conducting plates. Potentially I've got a dielectric sitting in there. And then how I build this, again, the geometry and what I've tucked in there defines the capacitance of the capacitor. If I want to think about the energy that's stored within the electric field now that builds up between those plates as I put charge on them, one of the ways that I can calculate that energy is 1/2 times the capacitance times the potential difference between the plates squared. So here's one way that I can calculate the energy that I've stored in my capacitor. Now we've talked about the fundamental equation for that capacitor, and here it is written in terms of C. C equals Q over V. And so part of what this is telling us, of course, is that the capacitance is a measure of how much charge you can store per the potential difference between your plates. Or one additional thing that I'll just go ahead and emphasize now, and we'll come back to in a second, is notice that my energy depends on the potential difference between the plates squared. The capacitance is inversely proportional to the potential difference between the plates. So I've got a V squared here in terms of calculating out the stored energy, and I've got a V on the bottom in terms of my ratio that defines the capacitance. We'll come back to that in a second. Inductors. Well, we said that you build an inductor by winding your wire around some cylinder. And again, that cylinder can effectively be empty, so you've got an air core, or you can have iron in that cylinder, and then you've got an iron core. So again, based on how you've built your inductor, that's going to determine what its inductance is. The current's going to generate a magnetic field. We can store energy within that magnetic field, and so the energy that we can store inside our inductor we calculate as 1/2 times the inductance times the current flowing through the inductor squared. So the first thing I'll highlight is, notice that structurally the equation for the energy stored in the magnetic field of the inductor is structurally very similar to the equation for the electrical energy stored in the capacitor. Instead of 1/2 CV squared, I got 1/2, my C becomes an L, and again my V becomes an I. When I think about what the inductance is a measure of, again, the fundamental equation for inductance I can think of as phi equals Li, and if I rearrange that in terms of the inductance L, it's telling me that it's the magnetic flux per current value. Notice the energy, again, depends on the current squared. The inductance has the current in the bottom of that fraction. So just like we had C equals Q over V, we've got L equals phi over I, and again you're seeing the same term that was squared up here sitting in the bottom of the fraction down there. We'll talk about that a little bit more on the next slide. What does this mean? Again, let's start by thinking about the defining equation. And so for a capacitor, I know that that's Q equals CV. And so all I've done is take my Q equals CV and then said, well, I just want to think about how that equation changes with respect to time. And so that's the change with respect to time on the left-hand side, change with respect to time on the right. Of course, the capacitance, that doesn't change, right? That's fixed as soon as I build my capacitor. So I can pull that out, and so I'm left with delta Q over delta T, which is the current, is equal to the capacitance times delta V over delta T. And so that may not seem very illuminating, but there's actually some really important information that's sitting in there that equation's trying to tell us. And so fundamentally what this equation means is capacitors resist changes in voltage. Another way to think about that is this change in voltage has to occur over some change in time. You can think about that as, where does the change in voltage come from? It comes because you put more charge onto the plates, and that simply takes time. So capacitors resist changes in voltage. As you put more charge onto the plate, they are going to try and generate a back EMF that resists changing potential difference between the plates. Current, on the other hand, can change quickly with a capacitor. The other thing that we want to emphasize for each of these is how they behave at the instant you close the switch and after you've waited a long time for your circuit. So capacitors, at the instant you close the switch, a capacitor acts like a wire. Once a capacitor becomes fully charged, it acts like a broken wire. So again, at that point, it's generating a back EMF that prevents current flow down the branch of the circuit where the capacitor is, so it's effectively acting like a broken wire. So what I want to do is I want to think about these same sort of ideas, but for inductors. Well, I know the defining equation for an inductor is phi equals Li, right? So the magnetic flux is equal to the inductance times the current. Again, if I think about how that changes with respect to time, over on the left-hand side of the equation, that gives me that the change of the magnetic flux with respect to time, which is equal to the induced EMF, that's got to be equal to, on the right-hand side, the inductance doesn't change because, again, that's fixed once I build my inductor, and I'm left with the change in current with respect to time. And so we'll make a similar argument here that we made in talking about the capacitors. How I want to interpret this equation is it says that inductors resist changes in current. Because of electromagnetic induction, when you change the current, it changes the magnetic flux. The change in magnetic flux induces an EMF that's designed to oppose that change in the current. So inductors resist changes in current in the same way that capacitors resist changes in voltage. The voltage for an inductor can change quickly, but it takes time for the current to change because an inductor will act to prevent that. Again, if we think about what's going on at the instant we close the switch and after we've waited for our circuit to reach its steady state, this is basically what these two values of 0 and as t approaches infinity means. At t equals 0, we said the inductor acts like a broken wire. Again, it's generating a back EMF to oppose exactly whatever change of the current you're trying to create. But once it adjusts to that change in the current, as t approaches infinity, the inductor acts like a wire. So the other interesting detail in terms of similarities here, we talked about similarities with energy and the way it's calculated. We've talked about similarities in terms of what the defining equation is trying to tell us is easy and hard to change with each of these elements. And again, what we see is it switches. The other thing that switches is how they behave at the instant you close your circuit and once your circuit's reached a steady state situation. At t equals 0, your capacitor acts like a wire. Current flows through it, no problem. Your inductor acts like a broken wire. No current flows down that branch where the inductor is. Once they reach steady state, on the other hand, it's now your capacitor that acts like a broken wire no current down that branch, and your inductor acts like a wire. As your circuit settles down with an inductor, the inductor basically just behaves like a wire, carries current, no problem. So hopefully, seeing some of these similarities and differences will make thinking about an inductor and the problems that we're going to do with inductors will help us relate those back to problems we already know how to do with capacitors. And so ideally, we'll make those easier to think about and get the right answers.